carbon compounds. Right at the end of the last lecture, you should remember that I was talking about oxidation, and I was telling you how you can oxidize an alcohol to an aldehyde, and for that purpose one of the many reagents that can be used is a reagent called PCC, pyridinium chlorochromate, and I drew up the structure for you last time. What I want to do now is to tell you how to oxidize an how to oxidize an alcohol right up to the level of a carboxylic acid, because if I can just refresh your memory, if you have an alcohol and you oxidize it, the first thing that you get is the aldehyde. And if you oxidize that further, then the next level of oxidation is the carboxylic acid. And so you know how to do the first step. You use pyridinium chlorochromate, but I haven't yet told you how to do the second step. And so this is the acid. The second step can be done with potassium permanganate. You can use either potassium permanganate in alkaline potassium permanganate, or you can use chromic acid. That's not chromic acid. Chromic acid is usually made by taking chromium trioxide and dilute sulfuric acid. And that is actually called the Jones reagent. It's named after an Englishman called Jones. He was actually born in Wales, Sir Ewart Jones, Professor of Chemistry at Oxford University. Now, how does this happen? Well, we're not going to go into too much of the detail, but I can give you some idea. And what I will do is to tell you how the the chromic acid procedure works. I'm not going to go into the potassium permanganate procedure. It's a very complicated mechanism, and you probably don't want to know about it. But the chromium trioxide mechanism is at least one of the possible mechanisms, is much easier to understand. But before I do that, let me just give you a typical example. If you take, let's say, this compound and you treat it with chromic acid, what you will get is the acid. And if you treat it with alkaline KMnO4, what you will get is the salt of the acid, and if you then treat that with acid, you will get the carboxylic acid. I assume you know that if you take the salt of a carboxylic acid, say sodium acetate, and you add acid to it, a strong mineral acid, you will get the organic acid. So if you take this compound and you add HCl, you will get that plus sodium chloride. And so when you use alkaline potassium permanganate, what's happening is that you get the salt. If you're using potassium hydroxide as the alkali, you get potassium salt. And in order to go from the salt to the carboxylic acid, you need to add acid. So there are two reagents for you to oxidize an alcohol to an acid. Now, tell you about the mechanism for chromium trioxide, because I just told you that I'm not going to give you the potassium mechanism, terribly complex, and I didn't think you'd like to know it. The chromium mechanism, the chromic acid mechanism, is also not straightforward, but at least it's easy to write down a plausible mechanism. Before I do that, I just want to tell you that the Jones reagent can also be used to oxidize secondary alcohols to ketones. So, for example, if I have this secondary alcohol, and this would be called cyclooctanol, you know from previous information I've given you that an alcohol, the name of an alcohol ends in OL. Ethanol, methanol, propanol, butanol, cyclohexanol, cycloheptanol, cyclooctanol. So the ol tells you it's an alcohol, and the cyclo tells you there's a cyclic structure, and the octan part tells you that the cyclic structure has 8 atoms. You all know that oct means 8, because all of you probably heard of a creature called, horrible creature called an octopus. Some of you may have seen them. I don't like them. Now I need to tell you about the mechanism. Now, before I tell you about the mechanism, I should complete this. So this now is the ketone. I've oxidized this alcohol to a ketone. And you notice what I've done, if you compare the picture of the alcohol with the picture of the ketone, the carbon bearing the OH group has a hydrogen on it, one hydrogen, which has now disappeared. When I go from this primary alcohol and oxidize it, the first step results in the disappearance of one of these hydrogens. Just like this hydrogen disappeared, one of these now disappear. And when I go from here to the acid, the remaining hydrogen disappears. So these oxidations are in effect a successive replacement of hydrogen that's on the carbon carrying the OH group. Now I need to tell you the mechanism of the chromium trioxide oxidation. To do that, I should clean the board. These chromic acid, chromium trioxide oxidations, quite interesting. The reagent is a sort of an orangey red, but when the oxidizing agent, the chromium, has done its job, it changes color to green. And so you know when the reaction is over. Now, I don't know what the police use these days, but many years ago, at least in England, if they wanted to find out if you'd been drinking, they would ask you to blow into a tube. And that tube has the chromium-6 reagent packed inside it. And as you blew down the tube, all the vapors of the champagne would go down the tube that contains ethanol, would be oxidized. And the chromium would change color to green. So if the whole tube became green, they knew there was a lot of alcohol in your breath. They put you in the back of a paddy wagon and took you to local police station. And if only a short length of the tube became green, they could calibrate, if the tube was calibrated, they had an idea of how much alcohol there was in your breath. What they do now, I don't know. I suspect it's much more sophisticated and more accurate. But let me show you how these oxidations with chromium work. At least I can give you a simple mechanism, so it isn't just a memorization business for you. So let's take a secondary alcohol. Here it is. And let me take chromic acid. And what I'm going to do is I'm going to allow the alcohol to react with the chromium in the way that I've shown. And water come along and replace that. And what I'm going to do, I think, is I'm going to also do this. So what I end up with Can you at the back see this writing? Is it dark enough? You sure? Okay, because these pens seem to be running out. Let's see if I've got a brand new one. So all I've done here is I put a proton on this oxygen. I've used these electrons to move here and at the same time break this bond. And then I've taken this proton off that oxygen so that I can generate this double bond. I think you don't follow that, so let me do it again. I'm going to protonate one of these oxygens. There it is. I'm now going to use those electrons to dispel that piece. And then finally I'm going to use water to take off that. And so I can get to this stage quite easily. And now this book gives one mechanism which I suppose I ought to follow. There's another mechanism that I know about that's probably more accurate. But what these people do, what they claim happens, is that this goes in there and this picks up a proton. And if you follow that through, you will see okie doke. Hopefully I can remember it.
So then he's just doing this left
Well, in fact, it gives that. Okay, let me give you a moment to copy down what you regard as a horrendously complex arrow-pushing mechanism. In fact, it's very simple once you've practiced it hundreds of times, like I have. Okay. The next thing that happens, I'm going to rub out this arrow now. Hopefully I can rub this out. It's all in your book. We've got to here. If you follow this through, what has happened is that, and you can see now that this hydrogen on the carbon that carried the original OH group, this hydrogen is gone. Because the electrons in that bond have moved between the carbon and the oxygen to give you this double bond, this carbonyl group. So if you have a secondary alcohol and you treat it with chromic acid, this sequence of events happens. This has got a special name. This is a chromate ester. Now it's easy for you to understand that it should be called a chromate ester for the following reason. Here is an acid, a typical acid, acetic acid, and next to it I have written an ethyl ester and ethyl ester. And you can see in going from an acid to an ester, you replace the hydrogen on the oxygen by a carbon piece. Here it's replaced by ethyl. Well, a moment ago I wrote down chromic acid. And you can see that just like acetic acid, chromic acid has an OH group on an atom that has double bond to carbon. There's an OH group on an atom that has a double bond to oxygen. No, sorry. And if I want to make an ester of this, I replace this OH, or the H rather, by a carbon. And so when I made this compound, you see the H that was here is now replaced by carbon. Of course, I still have another OH that's similarly acidic, and so I could actually make a double ester. But the mechanism doesn't go through the double ester, it goes through the monoester. In exactly the same way with sulfuric acid, you can have a monoester, and you can also have a double ester. So the fact that it's called an ester should not be any surprise to you. It fits in nicely with what you know about acetic acid and ethyl acetate. It's just that the acid is a little bit different. So that's what happens when you oxidize a secondary alcohol. Now, the hydrogen on the carbon attached to the OH is lost, and that carbon becomes double bonded to the oxygen. That immediately tells you something. It tells you that if you've got a tertiary alcohol, in other words, an alcohol in which there is no hydrogen on the carbon carrying the OH group, you can't do this oxidation. So those things are stable to the oxidation process. They might undergo other processes if you use acidic conditions. In fact, that one would. It won't be oxidized in the way that I've described. It also allows you to understand why a primary alcohol can be oxidized not only to the aldehyde, by removal of one of the hydrogens on the carbon carrying the OH, but it can be oxidized further because, well, not because, I will show you how that happens. So let's take a primary alcohol. And we treat it with chromic acid. And the first thing that's going to happen is I'm going to get the aldehyde. But you need to remember something that I told you last lecture, I think. A carbonyl group is polarized in the sense that there's a slight negative build-up of charge density on the oxygen and a slight deficiency of charge density on the carbon, so that nucleophiles like to attack the carbon. Now, in this reaction mixture, there are quite a few nucleophiles. One of them is water. The whole thing is acidic, and so you can easily imagine this happening. will explain all this in nice detail now. Let me give you a little moment to catch up with the writing. What I've drawn on the board is a primary alcohol being oxidized by chromic acid first to the aldehyde. And the aldehyde, obviously, by definition, it has a carbonyl, and the carbonyl is attacked by water to give you first this species, which loses a proton. So now we have this, which is a hydrate of the aldehyde. Why is it called a hydrate? Because if you compare the formula of that stuff, the hydrate, with the formula of the aldehyde, you'll see that the difference is just H2O. And if you add H2O to something, you hydrate it. You know, you can go into a cosmetic counter of pharmacy and buy things like hydrating gel or this, that, and the other. It's supposed to be putting water on your skin or into your skin. You hydrate something. If you dehydrate it, you know, if you run into the lab in the morning because you're so keen to get to the lab, by the time you get to the lab, you're a bit thirsty, you're a bit dehydrated, which means you've lost some water. Now, this stuff, it has carbon carrying an OH, so it's some type of alcohol, and that carbon also has a hydrogen. And you know from what I've been telling you about secondary alcohols, that if you have such a situation, and you treat it with chromic acid, you lose the hydrogen on that carbon, and that carbon becomes double bonded to oxygen. Guess what's happened? We've lost the hydrogen on that carbon. It's double bonded to the oxygen. So that is how, at a very simple level, these chromium trioxide oxidations are mechanistically very complicated, but it's easier for these to write down a simple mechanism that will help you remember what's going on. So this oxidation is understandable in terms of the simple mechanism that I gave you. Now, why is it that with PCC, which is also a chromium-6 oxidizing agent, you do not get the acid? Well, the answer is that PCC is soluble in organic solvents like dichloromethane, and so there isn't any water there. Because there's no water there, you can't hydrate the aldehyde. If you could hydrate the aldehyde, it would go further. But when you use chromic acid, you're using an aqueous medium. So there's water there. So the aldehyde gets hydrated, just to a very small extent. The proportion depends on the aldehyde, but it's usually very, very small. But it doesn't matter. That small amount gets oxidized. Then another small amount's formed, and it gets oxidized, and quickly the whole lot's oxidized. So that's the story for oxidation of secondary alcohols. They go to ketones. Primary alcohols, if you use PCC and dichloromethane, it goes to an aldehyde. If you use chromic acid, it goes to the acid. And tertiary alcohols are stable. Now, you should do problem number 12.4, which is 12.05 in 9th edition. And that will give you some practice at these oxidations. Now, I'm going to tell you about something else now, and you might think I'm just changing gears and changing subjects, but I'm not, because I want to tell you about some other methods of making alcohols. And in order to tell you about that, I need to tell you a little bit about a reagent called the Grignard reagent, named after Victor Grignard.
Last class, it was the other guy. Or whoever, yeah, who did it. And then half the class was a video. It was a video on knowing cochlear implants. Just knowing how they work. And they even showed surgical videos. And it's they cut the guy open.
If you treat an alkyl halide, X is equal to iodine or bromine, sometimes chlorine, and this can be alkyl or aromatic. You will get a reagent that's written like this, but it behaves like this. It behaves as though there's a negative charge on the carbon. And that negative charge means certain things. One of the things that it means is that that stuff is a base. And so it can remove acidic hydrogens from compounds that have an acidic hydrogen. So if we take, let me do a specific example. If we take ethyl magnesium bromide and treat it either with water or with an alcohol, for example, what will happen is that the negative charge will attack the acidic hydrogen and give you that. So if you add a Grignard reagent to an alcohol, you'll get the hydrocarbon. So this actually tells you something. Supposing you need some hydrocarbon, we'll call it that, so R can be some complex stuff. And you don't have that hydrocarbon. But you go to the stockroom and you find that they do have the corresponding alcohol. So now you know what to do on the basis of what I've told you. You know, let's say with PBr3, that you can probably convert the alcohol into a bromide. And I just told you if you treat a bromide with magnesium in ether, you can make the Grignard reagent. And now you know that if you treat that with water, you will get the hydrocarbon. So this is now really the first instance where you can put together many of the things that I've taught you in the last dozen lectures. Because the main activity of organic chemistry is to make compounds. We all need various compounds to be made. Some of them are medicines, some of them are agrochemicals, some of them are perfumes, some of them are insecticides, some are fibers for clothing, some are dyes, some are insulators, some are plastics, all sorts of things, and somebody has to make them. And in order to make them, what you do, this is actually quite a simple example, although you probably regard it as horrendously complicated, so much memorization and so forth and so on. I've heard all these grumbles before. Of course, I also made the same grumbles when I was a student. This is an example of the sort of thought process that goes on in planning how to make a particular compound. You ask yourself, Is this compound available? Sometimes you can just get it from oil or something like that, but sometimes it isn't available. Then you have to ask yourself, what ways do I know of to make this particular compound? I mean, for example, it's very easy if you wanted a particular bromide and you didn't have that bromide to ask you, what ways do I know how to make a bromide? Well, one of the ways is from an alcohol. Another way is from NBS aligned delamination. Another way is to add HBr to a double bond. Another way would be to carry out a nucleophilic substitution with a bromide ion, and so on. Now, as you can appreciate, it becomes extremely complicated if you're making a molecule that's not simple. I mean, in your book, there are plenty of pictures of complicated structures, and they're not easy to make, because the number, I just gave you 4 or 5 ways of making a bromide. But if there are 4 or 5 ways of making an alcohol, then there may be 25 ways of getting the bromide. And if there are 4 ways of getting, making a carbanion, you know, the number of possibilities increases. So it's a very difficult business. Anyway, to get back to the Grignard reagent, it acts as a base. That means if you add a substance with an acidic hydrogen, that acidic hydrogen will be removed. And the very simple acidic hydrogen that I gave you is water and an alcohol. But there's another type of acidic hydrogen that you should be aware of, and from last term's lectures, you know that the hydrogen at the end of an acetylene is also acidic. And so if you have an acetylene, let's just take this, let's take this one. And you treat it, let's say, with methyl magnesium iodide for a change, what will happen is what I've drawn. The acidic hydrogen will be removed. Now, the reason for telling you about these Grignard reagents is that it now lets me tell you about some other ways of making alcohols. Because remember, we're talking about alcohols. Earlier today I told you how to oxidize them. Today I want to tell you a few methods about making them. So if you've got any terminal acetylene, that is acetylene at the end of the chain, that has a hydrogen therefore on triply bonded carbon, this bond can be broken in this way because that hydrogen is acidic. It's not as acidic as the hydrogen on the oxygen of acetic acid. It's a heck of a lot more acidic than the hydrogen on an ordinary hydrocarbon. Now, what are the ways in which you can use Grignard reagents in order to make alcohols? The first way is this. If you take an epoxide and you treat it with a Grignard reagent, you will get an alcohol, according to the process that I've drawn up on the board. And you can see that what has happened in that process is that the original carbon unit of the Grignard reagent has been extended by 2 carbons, because these are the 2 carbons that I've added, and they come obviously from the epoxide. Now that process is a nucleophilic displacement, which means that you actually know something about it. And what you know about it is this. Supposing I have an unsymmetrical epoxide, SN2 reactions generally prefer to attack at the less substituted end of a double bond. And so if I have this unsymmetrical epoxide, I will get the secondary alcohol that I've shown, because the attack will occur here and not at that position. So that's one of the ways of using a Grignard reagent to make an alcohol, which means this is one of the ways of converting a bromide or a chloride or an iodide into an alcohol. And what it does is it adds more carbon to the original Grignard reagent. So if you have a long alcohol, you know that you can make it from a somewhat shorter Grignard reagent by adding 2 carbons. There is another use of Grignard reagents to make alcohols, and it is by far the most common use, because it works beautifully, and I suspect you've done this in your laboratory course. And this method is the reaction of a Grignard reagent with a carbonyl compound. Now, there are several types of carbonyl compounds. So let me show you what happens for each of these types. These are the only types I'm going to mention. The first type is formaldehyde. Let's take ethyl magnesium bromide as an example and treat it with formaldehyde. Dilute HCl, and what you get. So you can see what's happened. We have generated a primary alcohol, and it has 1 more carbon than the Grignard reagent. So wherever you see a primary alcohol, it can be any primary alcohol under the sun. This compound. You know that in principle, you can chop it there, and this piece could come from formaldehyde. Now, of course, when I say any alcohol under the sun, if you're going to use this method, there mustn't be anything in here that is incompatible with the Grignard reagent. So there mustn't, for example, be another carbonyl group there, ketone. But I think you get the message. From this example, you can understand how a Grignard reagent corresponding to this piece can be chain extended by 1 carbon to give a primary alcohol. Let me remind you, this is a primary alcohol because the OH is on carbon that's attached directly to only 1 other carbon. Whereas this, to give you a strong comparison, is a tertiary alcohol because this hydroxyl is on carbon. It's actually 1, 2, 3. Or even we can put it like that. It's attached directly to one, directly to another, directly to a third. So this is a tertiary alcohol. This one's primary alcohol. So I've done now this one. You get a primary alcohol from formaldehyde. What about starting with an aldehyde itself? Now let me rub the whole one out. And let us take now, why don't we take this? So now I'm taking cyclohexyl magnesium bromide, which obviously I made from bromocyclohexane, or cyclohexyl bromide, and I'm going to write it a little bit differently. I'm going to put a minus charge there and a plus there, and this minus will go in here. And when I pour that into dilute HCl, what I get now is a secondary alcohol. So you can see that when you treat a Grignard reagent with an aldehyde, you get an alcohol, but sometimes you get a primary alcohol, and sometimes you get a secondary alcohol. And the times when you get a primary alcohol are those when the aldehyde is the simplest possible member, when it's formaldehyde. And the times when you get a secondary alcohol is every other case, every other aldehyde. So now you know something more than you think you know, because supposing you needed this compound on the basis of what I told you today. If you ask yourself, how can I make that compound? One of the answers has to be, I could make it by oxidizing the corresponding alcohol. It would be a secondary alcohol. So the next question is, how can I make this compound? And on the basis of what I've written on the board, obviously one of the things you could do is to make this bond by adding cyclohexyl magnesium bromide, or chloride or iodide, to an aldehyde. There are other ways as well. So you see here again, all these things that I've been telling you very recently, they all come together and allow you to plan routes to various compounds, some of them starting to look quite complicated in structure. So now I've done this one. Let me do the last one. Well, not the last one, the next one. Supposing I have ethyl magnesium bromide. I don't know why I keep using ethyl magnesium bromide today, probably because I've got a big bottle of the stuff upstairs in my lab. And I'm going to take a ketone. Well, why don't we take this ketone? And you can see, on the basis of the things I told you today, that that carbanion will attack the carbonyl, as I've indicated. And when I pour this into dilute hydrochloric acid, I will get that tertiary alcohol. So now you know that if you take a Grignard reagent and add it to a ketone, course, you get an alcohol, but this time it's a tertiary alcohol. There's some frowns of misunderstanding or incomprehension in the first few rows. This is a tertiary alcohol because this hydroxyl is on carbon attached directly to 1, 2, 3 other carbons. Is that all clear in front of you? Now, I said dilute hydrochloric acid. I said that for two reasons. One is, if you use very strong hydrochloric acid, the reaction is the quenching of the oxygen minus. It's very, very vigorous. So only a nutcase would do that. And the second thing is, you know that if you have an alcohol, especially a tertiary alcohol, you can carry out an acid-catalyzed dehydration. And so you quench that Grignard reaction at ice bath temperature with cold, dilute hydrochloric acid. Okay, I guess on Friday, if there is a class, is there a class on Friday?
Yes.